Let's go for the final section for spray combustion. And here, this is we are dealing with the ignition of liquid fuel sprays. Okay, I hope you remember we talked about the ignition for the premixtures, and we understand those kinds of ignition characteristics can be described by the so-called quenching distance or minimal ignition energy you may have from your spark, right? And the achievement on ignition based on the competition between the heat release by the chemical reactions and the heat loss through the thermal effect and the turbulent influence. Okay. Now, when you think about the ignition for the liquid fuel spray, that means that you need to add additionally influence coming from the uh, liquid fuel evaporation. Okay. Now, we try to bring this gasification process. Definitely, you believe in the process of ignition, the gasification process for the fuel droplet, they will produce additional heat loss, right? Okay. Now, think about the passage of the spark. Create a small and roughly spherical boring of air, which means that we supply the minimum we supply ignition energy, and this fireball has a high temperature and is sufficiently high to initiate the evaporation of fuel droplet and also to let the chemical reaction to be initiated. Okay. Now here they tell you the reaction times and mixing times are assumed infinite fast at first. Actually, this theory proposed by the Lefebvre, Ball and Lefebvre for heterogeneous mixtures. In our previous study, those kinds of ignition theory basically proposed by Ball and Lefebvre based on homogeneous mixtures. Now we extend to increase the liquid droplet into the homogeneous mixtures. Okay, in the beginning, they try to simplify the problem. They treat reaction rates and the mixing times are very fast, assume infinite fast. Therefore, any fuel vapor created within the spark kernel is instantly transformed into combustion products at a stoichiometric flame temperature. Okay, we do not think about a finite chemical reaction rate and a finite mixing time. Then the essential condition for propagation of spread kernel, that means that you initiate the ignition process, was depends on the balance between the rate of the heat generation by the fuel. Okay, they will generate the fuel vapor and create chemical reactions by mixing with oxygen and react. Okay, and if the rate of heat generation exceeds the rate of heat loss, I'm sorry, here there is the one word, the rate of heat loss. In this case, okay, when you think about the liquid fuel exists in your ignition area, then heat loss will get involved with the heat diffusion out based on the temperature difference from the ignition source to the surrounding. And the secondary, if you have a turbulent flow, turbulent diffusion will carry those kinds of turbulent AD will carry certain heat out of your ignition area. The third thing you need to think about the gasification coming from the liquid fuel. They do the based on these assumptions, they can estimate the quenching distance, or you can relate to the minimal ignition energy as we described. Minimal ignition energy is equal to Cp times delta T and the volume, the mass. That means the total enthalpy from the ignition source. Okay, and this is the pi divided by 6 times dq to the power of 3 that represent the volume of your spark kernel. And actually, the relationship already explained earlier for the Gaussian for the homogeneous mixtures. Okay, and the dq here can be described for stagnant mixtures and flowing mixtures separately. Now, I try to explain a little bit here. You can see compare with the previous estimation D, this is a mass diffusion, right? Okay, we have this represent some a diffusion process will bring a certain heat carry out. And there is the velocity fluctuation for the flowing mixtures. For stagnant mixtures, we do not consider fluctuation. But here, for the flowing mixtures, you need to think about the turbulent eddy. They will bring out of the certain amount heat from the ignition region. And additionally, here there is the natural log function of 1 plus s. S is a Spalding number, and you will find out this as a natural log function represents the contribution from the gasification of your droplet, right? Spalding number give you the idea about the balance between the driving force and the resistance for gasification. Okay. Here I need to mention that bring the there is a phi equilibrium ratio here, and for these two formula, phi is always smaller than 1 because phi we are talking about the initial condition for the ignition process. Initial condition means you just supply the liquid fuel to the ignition area, right? Then from the beginning, the gasification is very weak. Actually, you do not have too much fuel vapor exist in the ignition area. Then equilibrium ratio is very small, it's very thin, okay? And you should understand this equilibrium ratio should be smaller than 1, okay? And here, I'm sorry, D is the presenter droplet diameter. Okay, I'm sorry, I made, yeah, they did not bring the, yeah, actually in here, they do not, those kinds of correlation do not bring the diffusion coefficient into the, into the equation because they just have a small fuel vapor exist, and the thermal diffusion or mass diffusion out is very small. And the U, capital U, represent the air velocity. Okay, and they did the experiment, and it seems has a good result. But let's look at the experimental result and a comparison with theory, and to find out what is the discrepancy between them. The left-hand side represent the the required minimal ignition energy will depends on the equilibrium ratio and also the droplet size. Here you can see for different solving diameter of droplet size you have for the sprays. When you increase your equilibrium ratios, that means that if you have more liquid fuel supply, which means that even you have a large droplet, but since the total amount of liquid increase, then fuel vapor will be increased too. Then when you have more fuel vapor exists in the ignition area, then the minimal ignition will be reduced because it is easier to be ignited. Okay, you can see for these three cases for the three cases of different droplet diameter. And additionally, you will figure out if you have a larger droplet, okay, for example, 150 micron SMD, then you require a larger minimal ignition energy because they provide less fuel vapor for the ignition. Okay, and on the right-hand side here, oh, I need to mention here for these two experiments, actually they restrict to U equal to 0. That means they look at the results on, especially on the stagnant flow without a turbulent eddy influence. Okay. The right-hand side tell you they use different kinds of fuel from heavy fuel oil, diesel oil, gas oil, and isooctane, and they find out actually the minimal ignition energy required for different fuels, as you can see from the figures. If you if you change your fuel from isooctane to heavy fuel oil, actually you understand those fuel the differences between these three fuel different kinds of fuel. Basically they will have a different boiling points. For example, heavy fuel oil has a highest boiling point, means it is hard to be evaporated. Isooctane has a relatively smaller boiling point, it's easier to be evaporated. Then for the isooctane spread, if you may have a small minimal ignition energy because it is easier, the isooctane spread easier to be gasified to provide more fuel vapor for the ignition process. Okay, This is one point you can see from this figure. The second, you can see if you increase the pressure, actually minimum ignition energy decrease. Yeah, this is simply say that if you increase pressures, then you will increase the interactions of the fuel vapor with the oxygen. Then they will promote the collision rate. Then they will increase harmonious numbers to approaching to the ignition. Okay. But here, it seems there's still have a big discrepancy, especially for the very lean case. Okay, here for the figures in the left-hand side, there is a discrepancy between the experimental results and the theory. Then Bow and Lefebvre try to modify their predictions by introducing a modified model in 1981. They consider the effect of finite chemical reaction rate. This is a complete different with previous assumption. Infinite chemical reaction rate, right? Now, like they consider finite chemical reaction rates, okay? And they know this is a very significant for very well atomized label at low pressure and a low equilibrium ratio. For the ignition process, you should remember the spray environment. Usually, they have a lot of liquid droplets, and with less fuel vapor exists. If you do not have enough fuel vapor, that means that in the gas phase conditions, they are pretty much thin, and it is very hard to ignite it. Okay. The second one, the presence of fuel vapor in the mixture is flowing into the ignition zone. That means they try to bring those gases, as I mentioned, the flow into your ignition process. And remember, they try to bring the important contribution from the gas phase. I described the quenching distance formula before on the page of 3.14, and I forgot to tell you. Actually, they just give you the formula without consider the detailed influence coming from the heat loss based on the gaseous mixture as we described earlier. But now the modified model, they bring the very important alpha represents thermal diffusibility, as we remember, we emphasize. Okay, this is a thermal inference from the previous discussion on the homogeneous premixtures. Okay, now you bring the alpha into your consideration and try to look at the finite chemical reaction rate and described by the spotting number. Here there is a spotting number, and they bring the French speed, or name it French speed, into, because French speed represents the real. Let me see. You can see in the previous formula they do not bring the original French speed. Okay, and here this is the French speed represents the gaseous behavior. Okay, now and those French speed basically is defined by the finite chemical reaction measure from the experiment, and the correlation will give you this very good formula, and the final result is here. Ball and Lefebvre published paper in 1980, 83, 81, and they give you the comparison. For example, the left-hand side, they consider the heavy fuel oil and without flowing. This is a non-flowing experiment, and they change the equilibrium ratio, and they do the measurement of minimal ignition energy for different spray with different droplet radius. The SMD are different from the 40 micron, 100 micron, and the 150 micron. And you will find out the solid line represent the prediction by chemical efforts in crude, and the broken line represent the previous estimation by evaporation model. Then you will find out the experimental result is well agreed. Is in good agreement with the with the theory. Okay. They tell you as you reduce equilibrium ratios, and then you will have a smaller, or you will higher minimal ignition energy. That means under very thin conditions, you can not easily to ignite your spray. You need to have a high. You need to provide or supply the higher energy to initiate the ignition. Okay. The right hand side give you the understanding when you go to the flowing strings, U equal to 15 meter per second. That still give you the confidence for the modified theory. You can see the solid line is very closer to the experiment. Okay, for different fuel from heavy oil, diesel, gas oil, and isooctane. Now, which means they think the modified model that bring the finite chemical reaction rate, which represented by SL, is the French speed of the homogeneous mixtures. Then the result is a good agreement with the theory, between a good agreement between the theory and the experiments. Okay. Later on, so many studies focus on the ignition conditions of then including different kinds of consideration. I will give you several results, and you can think about the influence coming from different kinds of parameters. Depends on and looking at on the ignition performance. Okay, the first one, air pressure. As we described earlier, if you increase the pressure, actually the minimum ignition energy will decrease, because this is since the ignition process is fully controlled by the evaporation. Okay, if you have a high equilibrium ratio and the pressures in these situations, then the pressure will play important role. I think there is the yeah, we do not have additional experiment result to show you, but you can go further, go to the previous experiments. Yeah, this is a pressure increase, the minimum ignition energy reduced. Okay, and for the air temperature, I think this is easier to understand. If you increase the air temperatures, the preheatings on the droplets is increased, then minimum ignition energy will be reduced. For air velocity, if you increase the air velocities, okay, decrease the air velocity, then minimum ignition energy will decrease. If you decrease air velocity, means that you try to suppress the turbulent AD, carry out the thermal energy out of the ignition area, then the spray is easier to be ignited. Okay. This is a typical experiment. Tell you when you increase the flow velocities, then the minimum ignition energy is increased continuously for these four kinds of fuels. And the right hand side tell you the influence coming from the air temperature. When you have a higher temperature, for example here 350 K, then the minimum ignition energy will be reduced. Okay, and when you reduce the temperature, the minimum ignition increase. That means the spray is hard to be ignited. Turbulence, as we described, based on the average velocity of your flow. Large average velocity, you need to have a larger minimum ignition energy. Fuel type, as we described, depends on the fuel mortality or transport number. Okay, and also the droplet size you will have for the spray. And because for these two factors, actually they will control the evaporation rate. If you do not have a larger evaporation rate, then you cannot provide enough fuel vapor for ignition. Okay. Here there is two figures to let you to support our observation. For the right hand side, they calculate the spotting number. Okay, as we described that when you have a larger spotting number, that means the gasification process will be enhanced. Then the minimum ignition energy will be reduced for different kinds of fuel. And the left hand side give you the air fuel ratios for different kinds of ignition conditions. You can see if you have a I need to mention here, The horizontal axis represents the air-fuel ratio. Okay, that means that when you go to the right-hand side, small air-fuel ratio means that you are going to the more rich conditions. To the left-hand side, large value of air-fuel ratio. That means that you will go to the lean side, and you will find out when you go to the leaner. Okay, when you go to the leaner conditions, then the minimum ignition energy, for example, for given solving diameters, then you will require to have a larger minimum ignition energy. The variation of minimum ignition energy for given a solving diameter, when you have a horizontal line here, you can see you can go from the right hand side to the left hand side. That means you go from the rich to the lean. Okay, you will find out is go to the very lean side. You need to have a large ignition energy. Okay, here. Okay, and I think you can try to look at the variation on the parameter shown in this plot to understand those effects actually described earlier. Spread characteristics is another importance. Actually, you can see the solving diameter. If you have a larger solving diameter, then you require a larger minimum ignition energy for different fuel. And fuel temperature is also important. If you have a smaller fuel temperature, then it is hard to be ignite. Okay, then you need to have a larger fuel temperature, and you will have an easier ignite. The evaporation rate increase with fuel vapor temperature is definitely, you understand, partly because of higher mortality, but also because the final atomization due to the reduction in viscosity. And the left-hand side tell you the influence coming from the droplet size represented by solving diameter. You can see when you increase the solving diameter, the minimum ignition energy is increased. And when you increase air velocity, all the curve will shift to the left-hand side. That means with the they will go to the more narrow sites. You require a smaller solving diameters to produce to achieve the ignition, because air velocity higher air velocity will carry more heat loss, more heat out of the ignition regions. Okay. Now we end up with the introductions on spread combustions up to here, and we still have some times to go through the descriptions on combustion pollutants. I think this is very important, and I will try to give you some briefly introductions on the initiation of the combustion products, and I try to look at their details.